Okay, well, we're back at it. And now we are going to be looking at Module 3. There's just lots of stuff to cover here. So we're finally going to be getting into some of the things that you might have thought of we would be right off the bat talking about. We're going to talk about matter and elements. We're going to look at the idea of what makes up an atom. We're going to introduce you to the periodic chart of the elements. We're going to be using that periodic chart every module in a variety of ways, so get really used to that. And then we have several objectives. If I give you a periodic table, I'd like you to identify the elements according to the following, whether they are a metal or a non-metal, etc. And then we're going to go through that. And then we're just going to talk about compounds, naming them, their characteristics, whether they're ionic or covalent. We'll look at their abbreviations, and I want you to be able to, if I give you the abbreviations, a formula for a compound, to tell me what its name is. Or if I tell you what its name is, tell me what the abbreviation for the formula is. So that's what we're going to do. And this video will cover the entire module. I'm not going to break it up. So if it's kind of long, you can follow along with the parts that, what we're covering, and then come back and revisit it. So let's get at it. So I'm including a document that has these notes. I would encourage you to download the notes and fill in the blanks and follow and work on the problems. So we're going to start off by giving you an introduction to matter. So two different ideas about matter. At one point in time, some people thought that matter had a continuous nature. It was called the continuous theory of matter. And the idea behind that is you could take any substance and you could divide it into smaller and smaller pieces. The other idea, and it turns out to be the idea that is correct, is that matter is actually discontinuous. That matter is composed of tiny, indivisible particles. And we're going to call these atoms, and we'll look at that in a minute. But the idea is that if matter were continuous, you could take a piece of wood, for example, and divide it in half, and you would still have pieces of wood. Divide that piece of wood in smaller pieces, and you would still have smaller pieces of wood. What we found out that eventually, if you could keep dividing it into smaller and smaller pieces, eventually you would get down to individual atoms of carbon and oxygen and hydrogen. And those atoms, you couldn't divide them into smaller pieces. So that's the idea of the discontinuous theory of matter. And that's the theory that we now hold. All right, we're going to go on. I'm going to introduce you to the elements. So an element is any substance that cannot be decomposed into less massive substances. Decomposed. You can't break it down anymore. And compounds, those are substances that can be decomposed into what we call elements. And that's what these are by chemical means. So the difference between an element in a compound is that compounds can be decomposed into elements, but once you get to an elemental state, you've reached an individual atom, and you can't decompose it, at least not by chemical means. So that's a really quick introduction to the elements. Well, our first objective in this module is this, to state the basic postulates of Dalton's atomic theory. Dalton concluded that atoms are the fundamental building blocks of matter, and that all elements are composed of small particles called atoms. And he named them atoms because atom means you can't divide it. Atomos. That's the Greek there. The second thing he realizes is that all elements of the same element, they have exactly the same properties. So for example, one element of hydrogen, whether you take that element of hydrogen from the water, or whether you take an element of hydrogen from a piece of cellulose, wood, or from sugar, that the element hydrogen actually has the same properties. And atoms of different elements, well, they have different properties. So carbon is going to have different properties than nitrogen, than oxygen, than iron, than cobalt, or whatever. And then the last thing is this. Compounds are formed when atoms join together in simple whole number ratios. And what I mean by simple whole number ratios is that in this compound here, this is a water molecule. Well, there are 2 hydrogens for every 1 oxygen. That's a simple whole number ratio. It's not like you have 2.3 hydrogens for every 1.4 oxygens. It doesn't work that way. They're individual atoms, and then 2 hydrogen atoms combine with 1 oxygen atom to form that water molecule. Here's another compound we call calcium carbonate. Calcium carbonate has 1 atom of carbon, 1 atom of calcium, 1 atom of carbon, and 3 atoms of oxygen. 1, 1, and 3, simple whole number ratios. And you can look at the others to get an idea of what we mean by that. All right, we're just flying through our objectives. I love it. Let me introduce you to the periodic chart. This is where all of the stuff that we are interested in, it starts with this. So I'm going to introduce you first off to the view of the thing. You can see that there are all of these abbreviations of elements, and some of these you're going to need to memorize. You're going to need to memorize all of them in period 1, 2, and I would say probably period 3. And you're going to want to memorize them in order. Helium, hydrogen, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, just like that, and then potassium and calcium. Those are the only ones that you're going to actually have to know in their order. There'll be a few others that you'll learn along the way, like iron is Fe, Mn is manganese, nickel is Ni, copper is Cu, Zn is zinc. Here's some of them that are not so obvious. Gold is Au, Hg is mercury, Pb is lead. Those are not so obvious. I guess that's enough of that for now. So pointing out this, that the periodic chart has periods, periodic chart, and periods go across. And this is the n equals 1 period. Here is the n equals 2 period, goes across like that. N equals 3 period. Those are the periods. And they also have groups. What you'll find out is that all of these elements in this column right here, they have some things in common. And so we consider them a group. And matter of fact, these 2 groups right here, these 2 columns, they actually form a similar group. We have the alkali metals and the alkali earth metals right in there. Over here, we have, well, let me still talk about metals. Anything that you see here that's in this kind of a, I don't know, a tan color, those are all metals. And this group of metals in the middle here that fall under the Bs, those are a special kind of metals that we call transition metals. These metals over here are so far to the right, they're almost nonmetals. Matter of fact, sometimes they act like nonmetals, but we won't go into that. But anything that has this green color, those are nonmetals. And one of the things that you're going to have to do, if I give you an abbreviation or a name of a compound, I don't need you to memorize it at this point, but I need you to be able to look at the periodic chart and tell me whether it's a metal or a nonmetal. All of these elements over here are all metals, but notice hydrogen. Hydrogen is never a metal. It's a nonmetal. All right. So in some periodic charts, we'll even take that guy and stick him over here off to the right, just to keep him from being in the group that you might confuse with being metals. So that is a quick introduction to our metals, to our elements. We're not going to talk about this lanthide series that's down here. Those you can kind of see where this group fit in. They fit in between the 56 and the 71 right there, and the 88 and the 103. Isn't that kind of weird the way that happens? In our class, first year chemistry, we don't even get into this series. In advanced chemistry, we do. So metals, they all have that tan. Metalloids, I didn't actually give you that name, but these are elements that sometimes function as metals, sometimes function as nonmetals, and so we call them metalloids. And then the nonmetals are the green ones. So, quick introduction to the periodic chart. Any quiz that I give you, you'll always be able to have a periodic chart to work from, except for if I give you a quiz and I want you to tell me the name of the first, 20 or so elements, and then I won't give you the periodic chart for that. But that's be a unique thing. Let's look at some of the characteristics here. Periods are the groups of compounds in the same row. Groups or families, these are ones that are often in the same column or similar columns, and they exhibit similar physical and chemical properties. For example, these elements on the far, far right, we call them the halogens. And what makes them similar to each other is they're not very reactive with other elements. These guys here we call the halides, and they are very reactive with other elements. All of these we talked about were metals. Anyway, that's what we'll go with. So there's some characteristics of the metals. Metals are located, as you see, on the left-hand side of the periodic table, and they tend to be malleable, which means that you can bend them and they don't break. They're ductile, that means you can shape them. They're lustrous, which means that if you knock off the oxide layer, they tend to be shiny. They're good thermal and electrical conductors, which is why we use metals like copper in our wires. And once again, I will mention that even though hydrogen is off on this far side, it's above the table there, get a picture of it. Even though it's over there, that is not a metal, that's a non-metal, so keep that in mind. Non-metals, non-metallic elements or non-metal elements, they're located in the top right-hand side of the periodic table. They tend to be brittle, they are dull in appearance, and they don't conduct electricity or heat well. And of course, there are exceptions to all of these rules, but that's a good starting place. So there you have your introduction to the periodic chart of the elements. Our next objective is that if I give you a periodic table, I would like for you to be able to identify the elements according to whether they are metals, nonmetals, transition metals, halogens, noble gases, and then whatever period or family groups that we might be dealing with. So let's have a quick look at some of the practice problems for that. So for each of the following sets of elements, label each as a metal or a nonmetal, a transition metal, a halogen, or a noble gas. And so the only way to do it is to go right back up and look at that periodic chart of the elements and try to find some place where you find the TI in there. Look in there, and you can look in the transition metals, see if you find it in there, because that's where he is. That's where your titanium is. And so because it is in that middle section of metals, we're going to call that a transition metal. All right, let's look for another one. Fe, that represents iron. If you find element number 26, once again, that's right in that transition metal block. Look at another one, Ag. If you find silver, and Ag is number 47, all right, and once again, that's in that transition metal block. So each of those elements there are transition metals. Now let's look at B. We have Ne, which is neon, Kr, which is krypton, and Ze, or Xe, which is xenon. If you go all the way to the right, you'll notice that those are all in the column 8A, and they are called noble gases. And we'll do another one here. So C has F for fluorine, Br for bromine, and I for iodine. And look at column 7A. Those are all right in that column, and those are halogens. All right, now let's look at lithium, potassium, and Rb. I always forget what that guy's called. Rb is called rubidium. Rubidium. Those are all, if you look at them, those are all in column 1A. And those are metals. Look at magnesium, Mg, Sr, which would be strontium, and Ba, barium, Where do we find those guys? Well, those are all in column 2A. And so those are metals as well. So that's the kind of thing. If I give you a metal, or if I give you any element, I want you to be able to tell me whether it's a metal or a non-metal, whether it is a noble gas, whether it's a halogen. So look at the number 2. Which of the 2 following elements would you expect to show the greatest similarity in chemical properties? For that to be true, we're going to find 2 of these guys that are not in the same period, like going from left to right, but are in the same column, going up and down. So sodium is located way over here in column 1A, and argon is located way on the far side in column 8A, so I wouldn't expect those 2 to be very similar. And chlorine is located in 7A, so that's not a 1A or a 8A or and oxygen. Now oxygen is located in column 6A. Krypton, here we have something similar. Krypton is located in 8A. And so even though krypton and argon are separated by several elements in that same column, they're actually going to have some things in common. They're going to be noble gases. And P, phosphorus, is in column 5A, and so phosphorus isn't going to have anything in particular in common with any of these other elements. So the 2 would be argon and krypton. Let's look at this. How many metals are in the following list? P, phosphorus, magnesium, hydrogen, sodium, carbon, silver, and sulfur. How many of those are metals? In order to figure out who the metals are, just look on the periodic chart of the element, and all of the nonmetals are going to be far to the right-hand side, and the metals are going to be to the left of the jagged line that starts underneath boron and silicon and arsenic. So let's look at this. Metals. Well, P, that's in that far right block. That's element number 15, so that's not a metal. Magnesium, though, now there we go. That's column 2A. That's going to be a metal. Hydrogen, even though he's on the left side, remember, clearly not a metal, never a metal. Sodium, going to be in column 1A, so he's going to be a metal. Carbon is going to be way over in 4A. That is not going to be a metal. That's going to be a non-metal. Silver, well, it shouldn't surprise you that silver is a metal. And S, sulfur, is in column 6A. So out of these, we have 1, 2, 3 metals: magnesium, sodium, and silver. So if we wanted to determine, we're going to look at the family or the group that we could talk about. Silicon is found on the periodic chart. Look at your periodic chart and see if you can find silicon. It's going to be abbreviated Si. And silicon itself is not a metal. You'll see that. It's actually in the non-metal category. But it's in the same family as some metals that are. Because if you look underneath that, you notice that silicon has both lead under it and tin under it. And so let's look at this. Magnesium, that's not in the same family as silicon, nor is phosphorus, nor is carbon, which is not a metal. But look at that, sure enough, lead. Lead is in the same family as silicon. Oxygen is in a different family, it's over. So it's possible to also have a non-metal in the same period as strontium. Now, periods go from left to right. Families and groups go up and down. So let's see if we can find strontium anywhere. Strontium is element 38. So we find element 38, and that is in period or in row 1, 2, 3, 4, 5 down. So if we wanted to find a non-metal that was in that, we're going to go across that row, that period, and find something that is a non-metal. And we have 3 possibilities. One is xenon, one is iodine, and one is Te. I don't remember what Te is. Beryllium. And in that list, sure enough, iodine shows up. So that's the kind of thing I'm going to want you to be able to do. I'm going to want you to be able to give me a metal, identify it, to know which way periods go, which way families go, and the fact that elements that are in the same family, they have similar characteristics. So that's a real quick introduction to the periodic table. Okay, we're making progress. We made our way all the way through objective number 2. So let's move on to objective number 3. Given the number of elements in a compound, I would like for you to be able to abbreviate the name of the compound with the element's abbreviation. So for example, just this simple, that if I tell you to have a compound that has 2 hydrogen atoms, 1 sulfur atom, and 4 oxygen atoms, I want you to be able to give me the element, the compound's abbreviation by saying that's H2, 2 hydrogens, S1, and O4. That's what I'm looking for there. Here's another example. If I say that there is a compound that has 3 iron atoms in it and 1 carbon atom, I want you to say that the name of that compound is Fe3O. 3 irons, 1 carbon. If I tell you that there's a compound that has 1 carbon atom and 4 hydrogen atoms in it, I want you to say that that is CH4, not C4, but CH4. And when we write those, it's going to be a capital C, a capital H, and the 4 is a subscript. Just like up here, we had 2 hydrogens, 1 sulfur, and 4 oxygens. I would write that a capital H with a 2 as a subscript. Sulfur, I don't have to say a 1 is a subscript because it's just understood that there's 1 of them. But I would write an O for oxygen, and I would write a subscript for 4 for that. So that's all I'm asking for when I ask you to give me the abbreviated name of the compound. All right, let's look at another thing. One of the important classifications of matter is that it's either ionic or covalent. And you're going to be able to tell if a compound is ionic because an ionic compound is going to have 1 metal in it or a metal in it and a nonmetal. That's just by definition. And a covalent compound is one that has no metals in it at all. It's just going to have 2 or 3 or so many nonmetals in it. So, number 1, if a compound contains at least 1 metal atom and at least 1 nonmetal atom, what is that going to be? Well, that is going to be an ionic compound. So, for example, the compound called sodium chloride that we call salt, it has 1 metal, which is sodium, and one non-metal, which is chlorine, and we call that sodium chloride. If a compound is made up solely of nonmetals, in other words, it's things only on the far right side of the chart, that compound is called a covalent compound. And so a molecule like water, H2O, those are all on the far side of the those are all nonmetals, and they're on the far right side of the periodic chart. So let's look at it. We'll identify them and write the formulas. So once again, a metal plus a nonmetal is an ionic compound. Sodium chloride is an example of that. And nonmetals plus nonmetals give a covalent compound, and H2O would be an example of that. So I want you to look at these practice here. Which of the following would you expect to be ionic and which are covalent? In order to do that, we have to see if one of these is a metal and if the other one is a nonmetal for it to be ionic. So we're going to look for RB. Look at the periodic chart of the elements and try to find rubidium. It's element number 37. Okay, now is that guy a metal or a nonmetal? That guy is a metal because he's in the far left side. But oxygen, on the other hand, is in the nonmetal category. So that guy right there, that's going to be a covalent compound. Look at the next one. P2O5. P is phosphorus, and that's element number 15. O is oxygen, and that's element number 8. Those are both, look at that, they're both in the nonmetal category. So that's going to be a covalent compound. I'm going to leave the rest of these to try on your own. Magnesium chloride, oxygen fluoride, hydrogen bromide, and then this one is NH4Cl. We call that ammonium chloride, but we'll talk about why we call it that later. But still, you ought to be able to tell me whether that is an ionic or a covalent compound. So that gets us through objective 4. Now look at this, we're just flying through these objectives now. Objective 5. If I give you a compound's abbreviation, I'm going to want you to name the compound. And the other way around, if I give you the name of the compound, I want you to write the formula. So let's do this. We'll start with a compound like I give you KCl. And if we're going to name that, you start with the name of the first atom. So you're going to have to figure out what K stands for. And in this case, K stands for potassium. And so the name of this compound is going to start with the word potassium because it has potassium in the beginning of it. Then the next one, you take the next atom. Here we have a chlorine atom. And because it's the second atom in the name of that, or the second atom in that compound, you replace its ending. It's no longer be a chlorine ending. You're going to place it with an ide, and you're going to call that chloride. So we're going to call this element potassium chloride, KCl, potassium chloride. In addition to that, that's how we will name a lot of simple compounds. If you're going to name a covalent compound, this happens to be an ionic compound. If you're going to name any covalent compound, we're going to include some prefixes that describe how many of the different atoms make up the compound. So here I didn't bother to say that this was monopotassium monochloride. We don't do that in ionic compounds. But once we get to covalent compounds, we do want to say how many they are. So here, this carbon and oxygen, I'm still going to start with just the name of the first one, as it is, carbon. But when I talk about the oxide, I put the oxide ending on that, but I also tell me how many oxygens. So that would be carbon monoxide. So you're going to have to memorize these prefixes. And here, I'm still going to have the word phosphorus, just like here. I start with the name of the first atom, phosphorus, okay? But because this is a covalent compound, I'm going to have to tell you how many phosphoruses are a part of this compound. So I'm going to call this diphosphorus. And oxygen, I'm not going to call that diphosphorus oxygen. I'm going to call that diphosphorus oxide, but I'm also going to have to tell you how many oxygens are associated with that. So I'm going to call that diphosphorus pentaoxide. We'll look at one more here, and I think you can figure out the how to name these. But here I have boron tetrachloride. Here I have calcium boron trichloride. Sorry about that. Calcium tetrachloride. Phosphorus pentachloride. Anyway, that's how we name these compounds. And from here on out, if I give you any compound, I want you to be able to tell me to write out its name if I give you the abbreviation. And if I give you the name of it, like phosphorus pentachloride, I want you to be able to write the abbreviation. So we got to go both ways on that. So let's look at some examples of that. What would the formula be of calcium nitride? So the first thing we have to figure out, is this ionic or is it covalent? If it's ionic, I don't have to worry about telling you how many calciums and how many nitrogens are a part of it. And sure enough, it is ionic because I have a metal and a nonmetal. So calcium nitride, I'll write that formula as CaN. A capital C, lowercase a, and then a large n, because nitride, That's a nitrogen that I have switched from nitrogen to nitride. How about the next one? Write the name of the substance with the formula N2O4. First thing we have to do is figure out, is that ionic or is it covalent? Because if it's ionic, I don't have to tell you how many I have, how many of those nitrogens and how many oxygens I have. But if it's a covalent compound, I have to tell you that I have 2 nitrogens and 4 oxygens. And it turns out that this guy is a covalent compound because both nitrogen and oxygen are nonmetals. So if I write the name of this guy, I have to say dinitrogen tetraoxide. Dinitrogen tetraoxide. So we've kind of covered that pretty quickly, but you're going to get an awful lot of work over the next 2 semesters. And believe it or not, you'll identify these and name these kind of just like you do eating and breathing. It'll become very natural to you, even though it may seem a little bit foreign right now. But that's objective number 5. All right, we have objective 6 to do, and then we'll get to the one where we actually have to do a little bit of math, okay? But let's look at objective 6. This is going to be another pretty easy objective. If I give you a molecular formula like H3PO4, I want you to be able to tell me how many atoms of a given element are in the molecule. So even though there are 3 different elements in that, there's hydrogen, there's phosphorus, and oxygen, I'm only going to ask you for this. What's the ratio of hydrogen to oxygen in that? And my ratio is going to be 3 hydrogens for every 4 oxygens. So it's 3 to 4. You'll figure out why this is important a little bit later. If I want to know what the ratio of oxygen to hydrogen is in this compound, now this one's a little bit weird. So we write the formulas, the names of these compounds, kind of like we do algebra. So what this means is that I have 3 of these NH4 ions that are associated with this phosphate ion. So the way I figure out how many hydrogens I have is I take the subscript of hydrogen and multiply it by the number on the outside of those brackets. So in this compound, I really have 12 hydrogens associated with this compound. And I have 4 oxygens. So my ratio here is going to be 4 to 12. Now I can simplify that as a 1 to 3, which is probably the better way to do that. But the key thing that I want you to recognize is that if you see a formula written like this, don't freak out. It's just saying that there are 3 of these NH4 groups. We call them ammonium groups. 3 of them associated with 1 phosphate group, which is that PO4. Let's look at another one. I want to know what the ratio of aluminum atoms are to oxygen. And so that's Al to O. Now here I have 2 aluminum atoms that are associated with that molecule, and I have a total of 9 that are associated with this other side of it, because I have 3 inside the bracket times 3 outside. So here my ratio of aluminum to oxygen is going to be 2 to 9. All right, now I want to just do some real simple math. If I want to know how many oxygen atoms are in 400 molecules of H2SO3. So for every 1 molecule, I have 3 oxygens. And so that means I'm going to take 3 and multiply it by 400 to get the number of oxygen molecules there are in 400 molecules. So 3 times 400, 1,200 oxygen atoms. Look at this guy here. So vitamin C is a big old compound. Vitamin C has 6 carbons, 8 hydrogens, and 6 oxygens. They contain 9.5 times 10 to the 6 hydrogen atoms. That's a lot of hydrogen atoms, isn't it? But if I want to know how many molecules of vitamin C there are in that sample, I just figure out, okay, well, if I have 9.5 times 10 to the 6th of them, and there are 8 hydrogen atoms for every 1 vitamin C, I'll take that number, 9.5 times 10 to the 6th, and divide that by 8, and see what we come up with. All right, so I'm going to break out my calculator. You do the same thing. And it really helps if you have a calculator that you are comfortable entering in scientific notation. So I'm going to say 9.5 exponent to the 6th. Divide that by 8. And I come up with 1,187, or excuse me, take that back. I come up with 1,187,500 vitamin C molecules there are. See how that works? All right. Take a breath before we move into the last of our objectives. We're going to actually do a little more reasoning and a little more math in this one, so I've saved it to last. All right. Let's finish strong. One more objective and then we're done. This is the last video that you'll have to watch on Module 2. So let's So objective 7. We want to apply what is known as the law of conservation of mass. So let's talk about some of the definitions here. So the law of conservation of mass, or sometimes it's called the conservation of matter. What we're saying is this, that during a chemical reaction, the total mass before the reaction is identical to the total mass after the reaction. It doesn't change. We don't lose mass. We don't lose matter in any chemical reaction. And conservation, maybe actually that's the word that's supposed to go in there. That doesn't look like it makes sense to me. The reaction is, yeah, I'm still going to say is identical to the total mass after the reaction. Conservation means that something can neither be created nor destroyed. I guess we're just referring back to that word, not that blank. It can only change forms. So here it applies to matter or to mass. So for example, if I have 7.7 grams of sodium and 11.9 grams of chlorine, when I produce sodium chloride, it shouldn't shock you to know that if I take 7.7 plus 11.9, I'll come up with the number of grams of sodium chloride. And so I'll do that math with you. You do the same thing. Let's see if we can come up with the same number. 7.7 plus 7.7 plus 11.9 is 19.6. And we can use all of those digits because 19.6 is good to the tenths, and both of those are good to the tenths. So we're even following our significant figures rule. So that's the first idea, that if we add up all of the mass of our reactants, that will equal the mass of the products. Or let's say if I just gave you the mass of one of the reactants and the mass of the products, you could in turn subtract the mass of that reactant from the mass of those products, and you would come up with the same thing. You would come up with that 11.9. So that's what we mean by the law of conservation of mass. That's not too hard, is it? All right, let's look at another one. This is the law of constant composition. What this says is this, that the relative kinds and numbers of atoms are constant for a given compound. For example, water always has 2 hydrogens and 1 oxygen. If you have 2 hydrogens and 2 oxygens, that's not water anymore. That's hydrogen peroxide. If you have 3 hydrogens and 1 oxygen, well, that's not water either. That's the ammonium ion, or excuse me, the hydronium ion. So you as long as you have 2 hydrogens and 1 oxygen, that is going to be what water is made up of. So the law of multiple proportions says that if we have 2 elements, let's say A and B, and they combine to form more than one compound, and we're going to look at an example of nitrogen dioxide and dinitrogen oxide, okay? Those are 2 elements. They combine to form more than one compound. That the mass of B, which combines with the mass of A, is a ratio of small whole numbers. So we're going to be talking about how much, the mass, how much of B and how much of A, and we're going to compare them. So the first thing you notice in our example here is we're going to keep the mass of nitrogen the same. We're going to look at one of these that has a mass of both of these have 14 grams of nitrogen, but we're going to change the mass of oxygen. So in one of these compounds, there are 32 grams of oxygen, and in another compound, there are 8 grams of oxygen, here and here. And so what we know is that this ratio, this whole number ratio, 1 to 4, it's always going to end up being 32 divided by 8. You're always going to end up with a simple whole number ratio. And the reason for that is because each one of these nitrogen atoms has a certain amount of mass. All of the oxygen atoms have a certain amount of mass, so that if we know how many grams of oxygen there are in the two different compounds, then the ratio is always going to be a ratio of a whole number of the mass of the oxygen atoms. I probably could have said that a lot better, but hopefully you can kind of see this. So interesting thing about nitrogen and oxygen, there are 5 distinct oxides of nitrogen. And when we use the word oxides, what that means is that nitrogen combines with oxygen in 5 different ways. Those are oxides. And the weight of oxygen in combination with 14 grams of nitrogen, so we're still keeping our 14 grams of nitrogen the same. We can't change two things at the same time. They are in increasing order of 8 to 16, 24, 32, and 40. Or they have a ratio of 1, 2, 3, 4, and 5. So the law of multiple proportions states just that if A and B combine to form more than one compound, and what we're saying here is that nitrogen and oxygen combine to form 5 different compounds, all right, so that fits the bill, then the mass of B, which combines with the mass of A, is a ratio of a small whole number, all right? So you're going to have to know and be able to state all these laws in order to pass your Wiley's exam at the end of the module, and then solve problems using that. And I'll show you a couple of practice problems that you can look at and you figure out how to work your way through this. So a reaction proceeds according to the following equation. You have just some element A is going to combine with 3 of the B, and they're going to produce 2C and 2D. Now, if the reaction consumed 12 grams of A and yielded 8.5 grams of C and 11.2 grams of D, how many grams of B must have reacted? And so the way we're going to answer that question is, we know that on our product side, we have 12 grams of A, and we don't know how many grams of B, but we're going to figure that out. And don't let it trouble you that it says that there are 3 B, because we're just going to be concerned with the number of grams at this point. But they yield 8.5 grams of C and 11.2 grams of D. So in order to answer that question, I'm going to add 8.5 to 11.2, and let me break out my calculator, and I'll let you break out your calculator and do the same thing. 8.5 plus 11.2. I get a total of 19.7 grams. So if I subtract from that the mass of A, I'll come up with the mass of B. So I'm going to subtract from that 12.0 grams, and I come up with 7.7 grams. So I know that there had to be 7.7 grams of B that reacted with that. And that illustrates our law of conservation of matter. All right, now let's look at another question to see if we understood the law of multiple proportions. So if we are going to talk about a compound that illustrates the law of multiple proportions, both of the compounds we're looking at have to have the same elements in them. If they don't, then the law of multiple proportions doesn't apply. So here I have carbon, and that's not the same thing as calcium. So this is carbon dioxide, and this is calcium carbonate, and we're not going to be able to illustrate the law of multiple proportions because this compound here on the right would also have to have carbon and oxygen in it. All right, let's look at the next one. This one is HNO2 and nitrous acid and sulfuric acid, H2SO4. This one cannot illustrate the law of multiple proportions because they do not have the same elements in both compounds. This one's got hydrogen, nitrogen, oxygen. It's got hydrogen, sulfur, and oxygen. Now here, this one does. This one just has sulfur and oxygen, sulfur and oxygen. So that one would work. Sulfur dioxide and sulfur trioxide. Sodium chloride and calcium chloride, well, they wouldn't illustrate it either because they have sodium in one and calcium in the other. So that is about 50 minutes worth of an introduction or a summary to Module 3.